Welcome to the 7th lecture of EE311. In this lecture, we will finalize the single transistor amplifiers made by MOSFETs. In the previous lectures, we have seen common source with degeneration, common gate. And today we will complete the discussion on MOSFET single transistor amplifiers by discussing common drain amplifier. Common drain amplifier is also known as source follower. I will explain why in a couple of minutes. Here you see the general diagram of common drain amplifier. For biasing, an ideal current source is shown. And when you take a look at this structure, we have drain, gate, and source. And drain is AC-wise grounded, and that's why it's called as common drain amplifier. But in the previous lectures, I told you that this is not a practical schematic because in practice, you won't have this ideal current source. You have to provide biasing by some other means. And most common technique is using, of course, 4 resistor biasing. So instead of using this schematic, I'm gonna draw the same circuit with a more practical representation where we utilize 4 resistor biasing to this circuit. So we have R1 and R2. This part is for the signal. We have VDD. In here, you can directly connect VDD to the drain. But, in some applications, maybe you can see like some drawings like this. They will be the same. It's not going to make a big change as long as drain is AC-wise grounded. Even if you do not have this capacitor, let's say C2, still it's going to be a common drain amplifier. It will work similarly like a common drain amplifier. It's not going to change the results significantly as long as you get your input from the gate and you get your output from the source end. But to be consistent with the definitions, we make drain AC-wise grounded by means of this capacitor. And of course, C1, C2, C3 are isolation capacitors. They isolate AC and DC from each other, like in the previous cases. I think you are familiar with it. We will apply the same procedure. We have to do DC analysis for the DC analysis is the first step, and you do DC analysis for, of course, finding operating point of the transistor. Of course, for MOSFET, you have to ensure that it's operating in saturation. The second thing is, after verification of the operation point, you need to find the small signal parameters. Which are R0 and GM. And these are the formulas for R0 and GM, as you may remember from the previous lectures. So this thing is straightforward, and if you take a look at it, the DC equivalent circuit is exactly the same with previous cases. You have 4 bias network for biasing the transistor. If you open all the capacitors, so I can say that it's exactly the same with previous amplifiers. Okay, so this thing is quite straightforward, I guess. Now let's apply AC analysis, and for the AC analysis I'm going to use this circuit B, but you will get similar results if you use A. As I said, the results may not change significantly, but The only difference in between these two circuits is that B is more practical, A is more like, um, book-wise schematic. But let's do the AC analysis for the circuit B. And as you see, the most critical thing, put the gate names first. Put the transistor port names first. Drain is AC was grounded, and there were R3, and R3 was shorted by means of C2. And what we have is R1 and R2 in parallel. C1 is shorted in here, and at the output C3 is shorted, so we end up with this circuit. And when we need to find three important parameters, of course: Rin, AV, and Rout. And I told you in the previous lecture that for Rin and AV calculation, only for Rin and AV calculation, if R0 is problematic, you can ignore it. But as you see, one end of R0 is grounded, so it doesn't create any extra complexity in mathematical calculations, so you don't need to ignore it. So in this case, you don't need to ignore R0 for any calculation. Let's find Rin. Let's start with the easiest part. So while finding Rin, you exclude Rs, the signal resistance. We name it as R signal in the previous slides. You don't need to take it into account, and you shouldn't, of course. So when you take a look at from here, you see infinite impedance. Without even making too many calculations, the input resistance can be written as R1 in parallel with R2. If you have any difficulty in finding this Rin, what you should do is just apply Vx, find Ix passing through it. But in this case, most of the time when you are dealing with MOSFET, it is very easy because input of MOSFET is at infinite impedance. For finding gain, I need to write V out in terms of VGS first of all. And for that purpose, what I can do is I can take this R0 and connect it in here. It doesn't change anything. Why? Because one end is already grounded, the other part is at source. So this is not going to change anything basically. In that case, you can write V out as VO or V out, whatever you name, will be equal to GM-VGS R0 in parallel with R4 in parallel with RL. Note that the current direction is consistent with the voltage polarity, so the sign is positive. Now I need to find VGS in terms of V signal. VGS is equal to VG minus VS. VG, I hope you can directly see it. It's going to be Rin divided by Rin plus R signal times V signal. There is a resistive voltage division in here. So VGS is equal to Rin divided by Rin plus R signal times V signal minus Vs. And this voltage is equal to output voltage. So in fact, this is equal to V out, which we have found before. So I can write it as GMVGS R0 in parallel with R4 in parallel with RL. So if you take this part on left and solve accordingly, the final result will be VGS will be equal to V signal times Rin divided by Rin plus R signal times 1 over 1 plus GM R0 R4 RL. And if you put this thing, if you put this expression in here, the final result will be Rin divided by Rin plus R signal times Gm R0 R4 Rl divided by 1 plus Gm R0 R4 Rl. The derivation is straightforward. This part seems a bit complicated, but it's just like a simple derivation. And the result is interesting in different terms. Like, first of all, it's positive, which means that the common drain amplifier is a non-inverting amplifier. So input and output are at the same phase. So the first thing that we should notice from this result is that common drain is a non-inverting amplifier. Input and output will have the same phase. The second thing is that when you take a look at this expression, this part is less than 1 definitely, and this part is less than 1. So this means that your gain is less than 1. AV of common drain amplifier is definitely less than 1. So this is somehow interesting because we always want large gain, but now we made an amplifier which has a gain of less than 1. So what we can do in this part is you want to maximize it, like by doing a good design. A good design means that AV of CD should be close to 1. It's going to be definitely less than 1, but you want to have it like 0.99 or 0.90 or as much as you can. And to be able to do that, of course, you have two options, two things to do. First of all, Rin should be much larger than our signal, okay? And you want the second thing, for making the second part as close as possible to 1, you want 1 much less than Gm times the total resistance over there. So you want to make this thing much larger than 1. If you can do that, then you can achieve the largest gain possible with common drain amplifier, which is like at most unity. So it provides in the best condition a unity gain. So you apply some input in here, you got the same input at the output. Let's say that you have some sinusoid in here with a peak of 1, let's say. In here, the best thing that you can have is like 0.99 with the same phase and the same signal. And that's why it's called a source follower, like source is following the gate. You have the same output for a good design. For a bad design, of course, you are losing the amplitude significantly if you cannot make this thing close to 1 or this one close to 1. So you are going to lose the signal significantly, but the purpose is making a buffer in here, a voltage buffer with a unity gain. So for that purpose, you want to make this thing as large as possible. Use like giga ohm resistance if possible, like in here, and try to make this term much larger than 1. Here I made a mistake, so it's not plus, but it should be in parallel. So you want to make this part larger than 1. And this thing is a voltage buffer. Of course, if the design is good. A good design means that AV is close to 1, of course. And let's find the output resistance of this thing. Maybe I can add a page in here. So let's find the output resistance. Rout is the resistance seen from here, and of course I want to keep this thing into account. I'm going to put Rout in here. It's not going to change anything mathematically. RL should be excluded from the circuit. So what I'm going to do is I'm going to apply Vx in here and try to find Ix passing through here. So Rout is in fact Vx divided by Ix, and Vx is R0 in parallel with R4 times Ix plus Gm VGS. This term is in fact this current plus this current passing through here. Note that R0 is not here anymore. So these two currents are adding up and flow through R0 and R4. And VGS, and when you are doing this thing, please do not forget that. Kill AC sources, which means that this Vs is shorted. If Vs is shorted, there is nothing to create a current in here, and therefore gate voltage is 0. So in this condition, gate is grounded. So VGS is equal to VG minus Vs, which is minus Vs, which is the term that I write just a few minutes ago, which is Vx, of course, minus Vx. And therefore, if I put this thing back in here, Vx will be equal to R0 in parallel with R4 times Ix minus Gm Vx, and then Vx divided by Ix can be defined as R0 in parallel with R4 divided by 1 plus Gm R0 in parallel with R4. Believe or not, this is in fact equal to 1 over Gm in parallel with R0 in parallel with R4. Please show it. Show this as an exercise. Let's be mathematically correct, so I'm going to show it like an equation. And I'm telling you that using T-model is advantageous when you have resistance at the source end, so you can utilize it in here, and in that case you will definitely see it in a much easier way. You are going to see this resistance in a much easier way. How? So let's use T-model instead. If you use T-model, let's name the transistor terminals properly. One over Gm. This is source. With the source I have R4 and RL, of course. And this is drain, GMVGS. This node is grounded. There is, of course, R0 in here. But since one end is grounded, I'm going to put that R0 in here. Okay, it's not going to change anything mathematically. So this is my model, my overall small signal model by using a T model for the transistor. Did I forget anything in here? Yes, I forgot something very important, something very critical, and if you forget this, your solution will not be correct, which is you have to put Ig is equal to 0 in here all the time. Never forget it. So in that case, if you take a look at the output resistance, your job is very easy. Why? For output resistance, you are looking from here, right? And you are killing all the AC sources. I kill this one. Again, there is nothing flowing in here, which means that gate is grounded. If gate is grounded, look at it like you have R4 in parallel with R0. And this 1 over Gm, when ungrounded, appears like it is in here. And when you take a look at R out, you will find the same result, 1 over Gm, R0, R4, without even doing any math. You just see it directly. And I'm going to give you a hint for MOSFET. Let's write it in here. This is a very important hint, in fact. For MOSFETs, if you are looking from source end, which means that if you are looking from, let's see a schematic. So when you are looking from here, from the source, when you are looking from here, the resistance that you see is always 1 over Gm. You see 1 over Gm resistance. So for the AC schematic, which means that when you are looking from here, you see always 1 over Gm resistance. So for a MOSFET source end, you see 1 over Gm resistance is coming from here. You are looking from source end. If you kill all the AC sources, gate is grounded, and therefore this thing will not affect your resistance, and you see directly this resistance, 1 over Gm resistance. And this T model is also helpful for finding the gain. Why? Because you can calculate gate voltage in terms of V signal. Since Ig is equal to 0, you just do some resistive voltage division in here, which is Rin divided by Rin plus R signal. So you know this voltage V gate first. Between gate and source, in fact, the output voltage is this one, source voltage. Again, you have a resistive voltage division. One resistance in here, the other is the whole resistance in here. And if you calculate it, you will find the overall voltage gain like we did in the previous slide. But one thing to be careful in here, never forget this Ig is equal to 0 term. Otherwise, you cannot write any of these equations. When you take a look at the output resistance, there is one more thing which is interesting. This 1 over Gm is low resistance. It is generally in the range of, let's say, like 10 to 100 ohms. So it's limiting the output resistance of the common drain amplifier, which means that common drain amplifier has low ROUT compared to the previous one. Remember that common source with degeneration, common gate amplifiers. When you take a look at the output resistance, you see always large output resistance. Only for common drain amplifier, since you are looking from the source end of your transistor, your output resistance is limited by 1 over Gm, which is a very low output resistance. And this is quite meaningful. Like, you want to use this thing like a buffer, right? You don't achieve any gain. it has like almost unity gain, but on the other hand, your output resistance is low, which means that you are matching your circuit to low load resistances. Remember the thing that I mentioned before. At the very beginning of the classes, I give you this example. You have some amplifier with multiple parts, and you have a low resistance load, which is like a speaker, let's say. So you have high gain, and a buffer asset. Buffer was an audio amplifier before. So if you do not have this audio amplifier or the buffer, when you connect this load resistance, it's going to change your gain significantly. Let's say that this is common source amplifier. Remember the voltage gain of the common source amplifier. It was like AV of CS was a negative one. Rin plus Rin over Rin plus R signal times Gm times Rd in parallel with RL. So if you do not have this buffer in here, your RL is directly this thing, which is 8 ohm. If it is 8 ohm, this term will be very small, and because of that, you cannot achieve a large gain with common source amplifier. But in this configuration, if you put a buffer, which is, let's say, a common drain amplifier, the input resistance is high. It was R1 in parallel with R2, and I told you to make it like giga ohm. Make it as large as possible. So instead of this RL, now you have this Rin. So common source can still have high gain, which is a good thing. But how I'm going to drive the RL? Well, the resistance that you see from here is 1 over Gm, something like that. So this common drain amplifier, it does not provide a gain. It has unity gain, or something slightly less than 1. But the main gain is still reserved. You can still hear a very loud music on your speaker by using this common drain amplifier as a buffer. It doesn't provide extra gain, but it only makes matching of this low load with low output resistance. This low load resistance does not affect the gain of previous stage at all. You put a buffer in between. You isolate them. This thing can still have large gain, and you can still hear a large or like high volume music on your speaker. So that's why we use common drain amplifier. It's a very good voltage buffer. Okay, so with this discussion, we complete the last type of single transistor MOS amplifiers. As you see, common gate is a good current buffer. Common drain is good voltage buffer. With common source and common source with degeneration, you achieve the voltage gain which is required. And eventually, we are going to combine them, make multi-stage amplifiers to achieve all the good things in a one single amplifier. But before then, let's discuss one thing that we haven't before. I keep saying that small signal and AC are two different things. All small signals are AC, but not all ACs are small signals. Okay, small signals are a subset of AC signals. And to be able to use a small signal model, that hybrid pi or T model, we have to ensure that input signal is low enough. What does this mean? This means that if I have a MOSFET, let's say gate is AC, source is AC bias grounded, and I apply an AC signal in here. To be able to use that hybrid pi model, this thing should be small. But what is the measure of being small? Which kind of signals can be accepted as small signals? Should it be like 1 microvolt, 1 nanovolt, 1 millivolt? That's the question. And it's related with the gain of the amplifiers. In fact, for any type of amplifier, let's say that you have such an amplifier. If you draw input versus output, we always assume that the gain is constant. But unfortunately, this is for linear amplifiers. Unfortunately, this is not true for all cases. In practice, in fact, when you take a look at the real drawing, it's not going to be a linear curve for the whole range, for the whole input and output range. Let's say this is output, this is the input. So this is the ideal case. In practice, of course, you will see some deviation, some saturation or whatever. If you zoom in, the linear range is limited. So small signal definition is coming from there. We are looking for that very small linear range where your amplifier operates like a linear amplifier. The same story can be applied to MOSFET. Think about a MOSFET. I keep telling you that a MOSFET is a transconductance amplifier, which means that if you have some VGS as the input, output is GM-VGS. MOSFET is a transconductance amplifier. Input is voltage, output is the drain current. However, this condition is valid for a small range. The actual characteristic of output current versus input voltage is something like this curve. So we have to make sure that this linear relation is satisfied. So how we are going to satisfy it? Mathematically, I can say that the drain current, in this notation you see both AC and DC. Why? Because I is small letter, D is capital. So it has both AC and DC. This is DC, this is AC. Okay. And in general, I can write it like Kn VGS minus VTN square. So this is saturation current. And please note that in saturation current expression, it should be valid both for DC and AC, and therefore this VGS also has two terms, DC and AC. So let's write it down like that. Kn divided by 2 VGS, the DC term, plus VGS AC term minus VTN squared, which is, in fact, if you separate it like, you can write the same thing as Kn divided by 2 VGS squared plus 2 VGS times VGS minus VTN plus VGS minus VTN squared. So it's like this. I take it as A. I take these two VGS minus VTN as B. So then the term will be A plus B squared. This is like A squared plus 2AB plus B squared. I didn't do any trick in here. This is just, typical polynomial expansion. So when you take a look at this term, in fact, this part and this multiplication is the DC current, right? So this introduces DC. So if you assume that this term is much, much, much smaller, like this condition, then you can ignore it, and the overall polynomial will simplify into this term. And this part, ID, DC current, this part will be the AC current. And there's something interesting in here. This Kn times VGS minus VT is in fact equal to 2KID in square root, which is GM. So this thing is equal to ID plus GM ID. So sorry, GM VGS. And this is consistent with what I'm saying in the previous slide. A transistor is a transconductance amplifier. Input is VGS and AC output current, ID current is GM times VGS. But look at it.
İlk önce iPhone'unun kilidini açman gerekiyor.
But look at it. While achieving this thing, I made an assumption. The assumption is this one. If I don't assume this thing, then the linearity is disturbed. Output current will have an undesired component. There will be other harmonics or whatever because of this thing. So to ensure linearity, I assume that this thing is much smaller than this one. So that's the key point for the small signal analysis. So for small signal operation, I can say that. Therefore, for small signal operation, 2 VGS minus VTN times VGS. By the way, VTN is equal to VT. Sorry for notations, but they are the same. Should be much, much smaller than VGS square. But now, how much larger is acceptable? That's the question. For most of the time, people say that like 10 times, being 10 times larger is good enough. So I'm gonna change this part with larger than, let's say, 10 times VGS. So if you make the necessary simplifications, you will find that VGS should be less than 0.2 VGS minus VTN for small signal operation. So this ensures that, this condition ensures linearity and therefore small signal operation. Okay, and this assumption of course may confuse your mind, like sometimes why you can say that why 10 but not 100, but 10 is good enough for most of the textbooks, so that people assume that like this much, being this much larger is satisfactory. So what does this mean? This means that if I have a common source amplifier, let's remember the schematic. Let's say that such a circuit is given to us, and let's say that like some numbers are provided, like Kn is given as, let's say, 10 milliamp per volt square, and VGS minus VTN from the DC bias is given as 1 volt. Since you're a good designer, I will assume that you choose Rin much larger than our signal. So now I can say that if this is VG voltage, in AC, VG is approximately equal to V signal. So the question is this: how much V signal can be applied while operating still in small signal region? So the answer is, I think, quite obvious. Source is AC wise grounded. Therefore, in fact, VGS is equal to VG minus VS, which is VG, which is approximately V signal. And for proper operation, VGS should be less than 0.2 VGS minus VTN, which is 0.2 volts. Therefore, V signal should be less than 0.2 volts. If you apply anything larger than this one, small signal is not valid anymore. Your system will not operate in small signal anymore. So here is a question. When you compare common source amplifier with common source with degeneration, which one has a better input small signal range? Let me write the question. When we compare common source and common source with degeneration, which one has larger input small signal range? So please think on it for a few minutes. But the answer is, of course, common source with degeneration. Why? Because for the previous amplifier, for common source amplifier, your input signal, assuming that Rin is much larger than our signal, directly appearing at gate voltage. Source is grounded, so V signal is directly equal to VGS voltage. Therefore, the small signal limitation directly affects V signal. But for common source with degeneration, you have a resistance in here, and this point is AC-wise grounded. So let's say this is degeneration resistance R. Now, VGS is not directly equal to V signal because V signal is shared between VGS and this new degeneration resistance. So if you have some value for VGS, you should multiply it with some term to find the input V signal. So common source with degeneration will always have larger small signal range, input small signal range. By the way, in the previous example, this Kn information is redundant. We are not using it for small signal calculation. I just give it, but at the end I noticed that we don't even need this Kn. So let me show that common source with degeneration in here very quickly. So look at this input part. I'm not drawing the full circuit. But assuming that R1 in parallel with R2 is much larger than our signal, this should be the case for a proper voltage amplifier. Let's say this is R4. So in that case, this node is AC wise grounded. Okay, so this gate voltage VG is almost equal to V signal. Now this V signal or V gate is equal to VGS plus the voltage across R4. So for small signal analysis, this VGS should be less than 0.2 VGS minus VTN. So you have some voltage headroom for V signal. V signal can be something larger. Okay, so in that case, common source with degeneration will always have a larger input small signal range. Please solve this thing. Solve this as an exercise and find and compare common source and common source with degeneration input small signal ranges. And if you cannot solve it, we can cover this thing in one of the recitation hours. But it's a very straightforward solution. Use T-model, and T-model will help you a lot. You are going to find some 1 over GM coefficient in the final expression, and you will show that V signal can be much larger than the common source small signal input range. Okay, I'm stopping here for this part of the course. In the next part, we will start bipolar transistor, single transistor amplifiers.